Alright, in this section 4.7 we talked about optimization problems. So we're talking about maximizing or minimizing certain things, maximizing profit, minimizing costs, things like that. So they talk about in here some steps involved in helping you to solve these problems. The first is you want to understand the problem, ask yourself what's known and unknown, what are the given conditions. Number two is probably the best part, is make sure you draw a good diagram, a good picture first. Notation is very important as well. You want to use labels that are useful, like A for area, H for height, T for time. And generally you want to, at some point you'll have to take the first derivative, but before you do that you want to write these things in terms of only one variable if you can. Alright, so let's look at example 1. You're talking about the area of a fenced off field, and you only need to come up with 3 sides because the fourth side is along a river, so you only have to fence in 3 parts. So these sides are going to call X, and this one you're going to call Y. And so the area is just X times Y, right? Area of a rectangle. But the perimeter is X plus Y, or 2X plus Y, and the problem tells us the perimeter is 2400. So when you solve this for Y, you get this, and now you can plug that into the area formula. And now you've got an equation in terms of only one variable. Now when you take the first derivative, set it equal to 0, solve, you get 600. And if you check the two endpoints, if you consider x to be greater than 0, but it has to be less than 1200 because you only have 2400 of square footage, so if you got 1200 and 1200, you're using up the entire fence and there's no fence left for y. So x cannot be bigger than 1200. So if you check both endpoints at 0 and 1200, you get 0 for the area. But if you check 600, which is the one we're guessing is the right answer, we get a maximum area of 720,000. Example 2, talking about a right cylinder. They say it holds 1,000 milliliters or 1 liter. And they ask you to come up with a way to minimize the area of the can. So you got area of the top and the bottom, which is pi r squared times 2. And you got 2 pi r circumference times h, which is the area of the side. When you unwind the side, it's got width of the circumference of your circle, and the length is your height. Alright, so now you've got your area here, but you also have the volume equals pi r squared h. We know that rule is also true. And so from there we can solve for h and plug that into here. And when we do that, our equation now is only in terms of one variable, r. And when you simplify it down, you get to here. Now when you take the first derivative and write it as one fraction, set it equal to 0, you get the top equals 0, the bottom equals 0, just gives you 0. That doesn't really help much. But the top, when you solve it, it gives you the cube root of 500 over the cube root of pi. And so then h equaling 1,000 over pi r squared, when you plug in what r is here and you square it, you get this here, which ends up being this guy here. And when you simplify it, it's basically ends up being 2 times the length of r. So for a minimum area and maximizing your volume, you want to make your height twice the radius. Alright. Example 3, they're talking about a parabola here. They say find a point on the parabola that's closest to the point 1, 4. So you want a point that's the shortest distance here. So we're using the distance formula with some point xy and this point 1, 4. So you get this. Now we can also say that our y here is equal to, our y squared equals 2x. That's the equation they give us. So we can solve that for x by dividing by 2. And so now when we got this guy in for x, we can plug that into where we had x before. And now we've got an equation in terms of only one variable, y. Now you can square both sides and you don't lose any chances of getting the correct answer. You still get a correct answer even though you square both sides. And now when you take the derivative of this guy, you get this, and simplify it down, you get to this guy here. And setting it equal to 0, you get y equals 2. Now we know y is in quadrant 1, so it's going to be positive, so you set it greater than 0, and 2 is your critical number, and you find out that is a minimum. It's minimizing your distance, so y equals 2 is the minimum. And plug in that for x, for y up here, and you get x equals 1/2 times 2 squared, which gives you also 2. And so your point is 2, 2. It is closest to that point there. Alright, number 4, there's a person, she's deciding whether to row over to this point C and run the 8 kilometers to B, or to row straight to B, or to do a combination of the two. And she wants to know what's the shortest amount of time. Her rowing rate is 6 kilometers per hour. Her running rate is 8 kilometers per hour. So we let x equals CD, this length here, and dB is just 8 minus x. AC we know is 3 from the original problem. And so you can use 3x and be able to figure out this side, square root of x squared plus 9, when you use Pythagorean theorem. Now we know distance equals rate times time, so time equals distance over rate. And the rowing time is the amount of time it takes them to cross the river divided by 6. The running time is the distance they run, which we know is 8 minus x, and they run at a rate of 8. And so their total time is this here. Alright. Now if x equals 0, she rows straight to C. If x equals 8, she rows straight to B. Now we take the first derivative of this guy, we get this, and we solve this by bringing the 1/8 over. We cross multiply, and we get to this guy here, and we cancel it 2, or divide by 6 and cancel it 2. Then we square both sides and solve it for x squared, and you eventually get down to here, and you take the square root, and now you got 9 over the square root of 7, or 3.4 kilometers. So it's the fastest way to get to where she wants is to row to 3.4 kilometers downstream and then run the rest of the way. Example 5 is not really a problem that you really want to look at. You don't need to know that problem. Let's look at some of the odd problems here. Well,